We are here to help.
In this video, we are going to learn how to solve non-homogeneous second-order linear differential equations with constant coefficients using the method of undetermined coefficients. A non-homogeneous second-order linear differential equation has the general form of a times the second derivative plus b times the first derivative plus c times the function equals a function of x or t, depending on the variable used. A, b, and c are all constants. The method of undetermined coefficients is generally only used when certain conditions are met. 1. When coefficients are all constant, and 2. When f of x belongs to a certain family of functions. Before we move into the conditions, let's talk about the solution in general. The solution of a non-homogeneous second-order differential equation is composed of two parts, the homogeneous or complementary solution and the particular solution. Suppose h of x is a solution to the homogeneous differential equation, and p of x is the particular solution. Then, the general solution of the non-homogeneous differential equation is the sum of the homogeneous and the particular solution. Now let's talk about the conditions under which undetermined coefficients is the best method to use. As we mentioned earlier, there are two conditions that we need to check before we can use this method. The first condition is that the coefficients must all be constant, and the second condition is that f of x belongs to a certain family of functions. The idea is if f of x is a certain type of function, we can make an educated guess to what the format of the particular solution may be, and solve for the undetermined coefficients in that guessed solution. Let's look at what type of function f of x can be and their corresponding particular solutions. If f of x is an exponential function, then we can assume that the particular solution has the general form a times e to the bx, where a is the undetermined coefficient. If f of x is a sine or cosine function, the particular solution will have the form a cos bx plus b sine bx, where a and b are the undetermined coefficients. If f of x is a polynomial function of degree n, we can assume the particular solution to also be a polynomial of degree n with undetermined coefficients. F of x can also be a combination of the above three functions multiplied together. A few examples include the product of an exponential function and a sine or cosine function, which would correspond to a general particular solution of the exponential and the sum of cosine and sine with undetermined coefficients a and b. If f of x is a product of an nth order polynomial and either sine or cos, then the particular solution will be the product of the polynomial function with undetermined coefficients, ai, with cosine, plus the product of the polynomial function with the undetermined coefficients bi with sine. These are not the only combinations for f of x, but from these examples we can easily determine what the particular solutions of the other combinations may be. Let's look at an example of how this method is executed. Consider the differential equation y double prime equals 4y prime minus 12y equals t times e to the 4t. As we can see, all coefficients are constant, and the differential equation is linear, since it doesn't contain any functions of y other than itself and its derivatives. In this example, f of t is t times e to the 4t. This classifies as a product of the polynomial function t and the exponential function e to the 4t. First, we solve for the homogeneous or complementary solution, h of t. We will discuss why we must always solve this before the particular solution later in the video. The characteristic equation that corresponds to this equation is m squared minus 4m minus 12 equals 0. Solving for m, we get m equals 6 and m equals negative 2. Since the roots are distinct and real, our homogeneous solution is h of t equals c1 times e to the 6t plus c2 times e to the negative 2t. Now we can solve for the particular solution. Since t is a polynomial function of degree 1, the corresponding particular solution would be at plus b, where a and b are unknown. The corresponding particular solution to e to the 4t would be c times e to the 4t, where c is unknown. Therefore, the particular solution for f of t will be at plus b times c times e to the power of 4t, where a, b, and c are all unknown. If we multiply c through, we can see that there are really only two constants. So we let AC be alpha and BC be beta. And we are left with P of t equals alpha t plus beta times e to the 4t. To solve for alpha and beta, we substitute the particular solution into the original differential equation. We leave the calculations of the derivatives to the viewer. Expanding and simplifying, we obtain the following equation. We want to make sure that once we are done simplifying, the coefficients of each term are constants. Now we can solve for alpha and beta by comparing the coefficients of like terms on the left and right side of the equation. We have terms t times e to the 4t on either side of the equation. Since the left-hand side must equal the right-hand side, their coefficients are equal. Similarly, the second term on the left-hand side does not have a like pair on the other side of the equal sign, so its coefficient must be 0. Solving for alpha and beta, we get alpha is negative 1 over 12, and beta is negative 1 over 36. Now we can substitute these back into P of t, and we have our particular solution, which we can simplify. The complete solution to our differential equation is therefore C1 e to the 6t plus C2 e to the negative 2t minus 3t minus 1 over 36 times e to the 4t. Now let's talk about why we always solve for the homogeneous solution before the particular solution. Consider the following example. F of x is 8 times e to the x, which means that the particular solution would have the form a times e to the x. But if we substitute this particular equation into the differential equation, we end up with 0 equals 8, which means that this particular solution is not in the right format. So how do we fix this problem? Let's look at the homogeneous solution. Observe that our assumption for the particular solution, a times e to the x, is already present in the homogeneous solution, which means that e to the x is a solution to the corresponding homogeneous differential equation. So how do we get around this issue? The homogeneous and particular solution must be linearly independent. We cannot change the homogeneous solution, but we can alter the format of the particular solution. If we multiply by x, we obtain linear independence with the homogeneous solution. Substituting this new particular solution into the differential equation and simplifying gives negative 3a e to the x equals 8 e to the x. And we get a equals negative 8 over 3. Therefore, the particular solution is negative 8 over 3x e to the x. To summarize, the method of undetermined coefficients is used to solve second-order linear non-homogeneous differential equations with constant coefficients. The non-homogeneous term, f of x, must fall into a particular category of functions. We always want to solve for the homogeneous solution first. If the homogeneous solution and the assumed particular solution share a term, then multiply the particular solution by x, or powers of x, until they are no longer linearly independent.